What we try to do with that is combining that human brain with computational power. And that's where generative design comes in. So, how can we describe generative design then? Well, this is the old way of design. There is one human, there is like one computer, and you get a limited design. You know already, before you start designing, you already know what the outcome will be. You will have like that typical chair. The only thing you need to do is try to design it, document it, and then use all kinds of tools to produce it. So you get these nice Scandinavian type of chair or American style, whatever you want to have. It's your limited design. So at Autodesk Research, they try to figure out what could be improved on that design of a specific chair. We already saw the result in the other presentation we had this morning. Now, if you look at this chair, it has a specific weight, it has a specific price. What could be done better? So, they put on some boundaries and some constraints, some design requirements into a product called Project Dreamcatcher. And it generated thousands of design options in the same time as in the old way a designer would need to describe only one. So you had all these kinds of results. We can discuss about the aesthetics of this chair, and maybe the comfort is not really well to sit on this. But imagine that you use this technology to create like the backbone of a building and then wrap it up with like nice facading so that you have like a really high performance design, but which is still an aesthetic design. So this is the new way of designing things, the new way of making things. We still have that one human, but we are using artificial intelligence algorithms together with the unlimited cloud computing technology. And that's where you get those 100s, where you get those thousands of design options. So, step by step, it's changing the world of design, and it gives you a lot of opportunities. It makes it possible for you to save time to do other things than trying to do all kinds of, let's say, repetitive tasks to find your optimal design. It boosts your creativity, so it democratizes your creativity actually. It saves money, of course, and you can create more and novel geometries. Okay, so let's have a look on how the people at this moment are using generative design, how our customers actually are using generative design in their world. So we already saw the example in the other presentation as well from Airbus on how they trimmed weight in their plane to make that division panel between the compartments in the airplanes. So the first example you saw was the result of the stresses with the massive plate. The second one was the optimized one. Now, what I did is trying to find out the boundaries, trying to find out the constraints that are necessary in here to give like that same strength of that panel within the airplane cabin. Putting all these boundaries into a product, into a technology that evaluates these boundaries, that evaluates all the design requirements, it gave this thing as a result, which was actually just a three-dimensional geometry which has to be connected with a 3D printer, and you got the result as you can see in here. So just assembling all of the things together gave them like a nice, similar division panel in the airplane, but which had a weight which is less, much more less than what we had in the initial airplanes. Now, Hackrot is a digital industrial company that develops design, engineering, and manufacturing pipelines that will drive the next industrial evolution. Now, what they've done in here, they outfitted a race car with dozens of sensors, and they driven it to the limit. So they use that race car to generate billions of data points. Now with these data points, they made it possible to find out the weakest points of that race car and to save material in the parts where we didn't even need material to make it stronger. So they generated a car which was much more better than the original one because it was at least lighter, but it still had the same strength of that original car, plus also it could still stay on the road and have the even better performance than the original car. This is a project from one of our interns at Autodesk, and he called it, Scott at least, he called it hacking the Howick. So the idea in here is to find a solution to create a very complex roof or a very complex building, whatever you want to have, with some parametric systems. So they are using identical elements, but with specific holes that are drilled in a specific place, and by combining them in several ways, we could create a very generative looking like design for that platform. In this case, they use Dynamo, or he used Dynamo, to generate the ideal solution for that, and to also make CSV outputs from it to drive the machine and to drill the holes in an automatic way. So it's a really exciting project that Scott has done in here, and he shared it with me to show it over here. So, how is generative design then applied on buildings? Okay, so this is an example that we applied on one of our own buildings. It's actually the new office of Autodesk in Toronto, in a new facility called Mars Innovation District. Together with a partner called The Living, they used a generative design approach to create, to design the new layout of the office space. So this is like an example of space planning. And we already use space planning as architects and all kinds of designs, but we never use like generative design technologies for it. So this is a research project, to be honest, so it's not like a product that is really existing. It's a technology that they've done in a customized way to get to that result. So this is the base plan of that office, where we have like access to the back house, where there's a reception, where we have like toilets. So these are like the fixed boundaries which you cannot fix. Which you cannot change. So they are fixed. You cannot say, let's move the toilets to another place because plumbing is already foreseen in that building, and so on. So at the same time, Autodesk Research also developed an architectural concept that an office space is like a city. So it has a wide variety of functions, and they should be provided in a diverse way. So in a way that a group of people with different needs and desires can live in that office space, in that city. So an office layout could be organized like that city, with major and minor streets, with more public spaces and less streets, or more streets, more private spaces, and so on. So a number of factors had to be considered to arrive at the design goals, to see how people wanted to live into that office space. So they asked all the employees what they had as a wish when they would work in an office space, what would be their best office space to live in, to work in. And they could identify like 8 different characteristics, let's call them. So they conducted studies against the existing King Street office they already had, to determine the best way to satisfy the design goals of the employees in that new space. So these are the 8 ones that were identified for it. And one which is very specific and very important in here is like the views to outside. You want to have like a feeling of freedom into your office space. So that was kind of most important part that they had identified in here. So to generate a viable space plan proposals with reliable results, The Living created a series of formulas to arrive at the optimal solutions. So a lot of formulas that are describing all these 8 requirements that the employees have identified, and to find an ideal solution for it. Besides all these requirements that were applied to the space, such as the team proximity and the amenity distribution, there is also like these 3 things that are important, where circulation is also one of the keys, actually, of success for this project. The result was lots of options. The product, the technology generated like thousands, again, millions of design options that were, well, meeting all the requirements that were asked. These 8 requirements with these 3 specific requirements like teams, proximity, and then the circulation that was important. So, yeah, then it's difficult, of course, if you have all these design options, you need to find the ideal one. So, scoring against those possibilities led to evaluations of satisfaction, for instance, against these 8 identified metrics again. Where specific diagrams you can find the ideal solution, where, for instance, if you say circulation is the most important one, then you take that second option, for instance, and then you discuss it with your people that will live in that office space, and you can see if you need to improve your solutions, yes or no. So this is the whole process shown in the video on how it's done in that full project. So you see the several floors. It's not only just that one floor, there are multiple floors in that office that need to be optimized. We already saw some example, that same example where Callan has shown it with that AI example, let's say, where the computer was talking. Now, at that moment, when Callan showed it, he told us, like, yeah, this is something for the future. Of course, with the computer talking to us. But this, where the office space has been generated, this is real. This is where we are at this moment. So that's not future. It's where the computer comes in and does it automatically for us. That's future. So in here, the human brain, the engineering expertise, combined with that artificial intelligent algorithms, could generate that ideal space for our new office. So that's a great example we have in here for our own office to show how these technologies can be used on buildings. So, what about computational design? There is a difference between generative design and computational design. Computational design is actually how you drive your design, how you apply some specific computational power on a design. You are not generating, or it's not automatically generated, you help generating it. So it's like the human interaction is much more in computational design than in generative design. But it's still giving you results that could have been reached also with generative design, and it's a bit more accessible if you want to use it in daily life or in your daily job. Now, let me show you just a few examples of that. We are not going to go like in a deep dive with Dynamo. If you want to do that, there are some hands-on labs during the day where Dynamo is also presented and where you can learn it. Now, this is a concept. It's a conceptual analysis, just a fictive building. Actually, the building that you see on the left is also generated with Dynamo. It's a footprint of diving goggles, so using an image and then extruding that image to have a building which has the shape of diving goggles, or at least the footprint of it has it. Now, the outer surface, as you can see on there, has a very strange design with large openings and smaller openings. Now, this geometry has been driven by analysis. So that's the computational design part that comes in. You want to get a design where you have like the outer or an inner mass, and on that inner mass you have sunlight. Now, if you drive in analysis throughout the whole year, you get those blue points, you get those red points representing results from solar analysis. Now, the more light you have on that inner wall, the smaller the opening has to be in that facade. So that's how that facade got generated. You take the results and then you generate a shell around that building based on these results. So it's not like estimating how large that opening should be and you draw the opening on that facade. No, you let it generate. You use computational design technology to get your facading. Another example is in structural engineering. For instance, you get like that specific roof, similar to the one that we saw from Hacking the Howick. And that roof needs to be supported with all kinds of structural elements, with beams and bracings and so on. Now, it's very difficult to make a design if you're not sure if the design requirements are fixed. If the architect tells to the engineer that something has to be changed on that roof, then the engineer has to rethink, has to reconfigure this whole structural design and has to, do a lot of rework. Now, when he makes like an intelligent system of his structural design, a computational system, then he can change it easily without having to think about it. Just incorporate the changes into the parameters, change the size of elements, change the value of specific parameters, and you get like a new structure. And this is how it works. On the left hand, you have Dynamo, where you build your intelligence. On the right hand, or now at this, you see the results of how the structure could look like in Revit in a computational designed way. Now, if you think a little bit further with this structure, what you also could do is you could connect analysis results to it and make informed decisions on that structural design based on your analysis results, where your computer is telling you, for instance, that you need more arcs to support the weight of that roof, because otherwise it would collapse. So that's more getting from computational design, getting in the way of generative design, where you use the analysis results. Now let's have a few more looks on generative design, but in this case we are going to use Project Fractal for it. Now, Project Fractal is a product that is it's still like some kind of what we call labs preview. So it's not a commercial product, but you can get access through the website of Fractal. So if you just Google on Fractal Live, then you get on the Autodesk link and you get access to this project. Now I'm going to show you some examples, some fictive examples that we build at Autodesk, and some examples of our customers on how they connected their design with Fractal. Now, Fractal is, to start a little bit with a small explanation, it's a cloud service. So it's a service that is connected with Dynamo Studio. You build your intelligence inside of Dynamo Studio. You build your computational design intelligence with a few parameters, and you send it to that cloud platform, and this is the result you get. Now, what we have in here is a curved roof, again, a double curved roof, and what I want to have as a design in here is a roof generated with panels that are flat. So I don't want to have any distorted panels, because that's difficult to manufacture. I want to have like regular panels. So what Dynamo does in here, it's evaluating that surface, it's generating panels on that surface, and then it's looking which of the panels are flat and which are having a planar deviation. So if you want to find your solution manually, that takes a lot of time. Because if you do it manually, you need to go through all the design options one by one, and you don't gain any time because you're constantly busy dragging your sliders to find your ideal solution. Now, if we plug it into Project Fractal, then we let the cloud do all this work. Let the cloud find all the solutions that are possible and then return some feedback, for instance, in this case, with colors. All the green solutions are the optimal solutions. The red ones are solutions which are totally not fitting in the design requirements. And with the parallel coordinate system that you have on top, that diagram, you can filter out your results, and you can even combine specific results to generate even more solutions until you find the ideal one. Now, it's not only about design. What about verifications of your current models? This is a structural model built up in Revit with a tower crane. Now, the challenge of this customer is that he wants to find the ideal position of that crane to make it possible to lift any of the elements without any restrictions. So there are lots of parameters for tower cranes. It's not just about the weight of one element, it's also about the position of that crane to deliver it on the building site and also to take it from the truck. So a lot of possible solutions again for the position of that crane. Project Fractal is calculating all its possible position, and it evaluates the elements to see if they can be lifted, if they can be delivered on site, if they even can be picked up from the truck that is delivering them over there. So these are a few solutions. As you can see, you can place that crane all over the site, not only at the front of the building, but could also be done at the back of that building. Now this saves a lot of time for that contractor to find out where to place that crane without having any problems on site after a few months of working. Now this is another example where Fractal is used, again in space planning. So this is a more accessible solution, let's say, than the one that I just showed you with the Mars project of the office building in Toronto. So this is a project that Autodesk did together with an architectural company in the States. And they used a space planning technology or space planning algorithms to find the ideal outline and layout, space layout for a hospital. So you have a lot of requirements when you're building hospitals, right? Now, in this case, it was somewhere July of last year, they tried to combine the hospital bed tower space program with a site outline. So you have like a limited site as well. And you cannot use the whole city, of course, to build a hospital. Okay, so it created a number of options. There are a few inputs. The first input was, of course, a CSV file with all the requirements for that hospitals. Like beds needs to be positioned at that side of the wall, the corridors need to have like a specific width, we can only have that amount of hospital rooms, or at least bedrooms in that specific zone of that hospital, and so on, and so on, and so on. The second input was an SAT file. An SAT file representing all the boundaries of that site. So you cannot extend the site boundaries to build up your hospital. It should be in that specific boundary. Now the process of this whole space planning, it starts with allocating your entry points. So that's where you indicate where you can enter the building, for instance, where you can exit the building, or where you need to exit the building. And then, besides that, the second part is where you assign the departments. So, where you can choose where to combine specific compartments, like where is carrying, where is the OK, where is reception, and so on. The third step is where they assign the programs inside specific departments. So each department also has its own requirements. And then the last one is where you create the circulation between the departments. So department assignment, requirements within the between all several departments. So that's the whole process that is used in here. Now this has been done initially in Dynamo. So they build up like a very specific package inside of Dynamo to create all the possible design options in 3D for that specific hospital. It's quite a powerful script that is used in here. And again, you need like manual interaction. It needs a lot of your human brain power, let's say, to explore all the possible design options. And you're not sure if you have reached the optimal solution for it. So what I've done, they also uploaded the whole design into Project Fractal again. And Project Fractal does all that time-consuming tasks for us. So it generates all the possible solutions, it gives us feedback, and using that feedback, they could find which solution was the optimal one, meeting the requirements that were stored in that Excel file. What you can see in here is that the feedback you get from Fractal can be anything, because you own it. You own the whole analysis within Dynamo. You set up what you want as a, what we call watch result, and you name it as you want it. It appears in that parallel coordinate diagram. The inputs are also something that you choose how to drive this whole design. So it's not Fractal deciding it for you, how it should look like. You can completely customize it in your own way and make your own analysis for it. So there were two major possible approaches in here that are in the same graph. So it's in exactly the same result you got from Fractal. And it encloses allocated spaces. That's the first thing, form follows function, or it fills an existing outline. It's the function that follows the form. So you can choose which of the possible solutions in here are best. So you would say like the bottom one is using all the possible ground you have on that site, but might be the most expensive solution. The top one is trying to save a little bit of ground over there, but might be the most complex solution because you need to squeeze in all the rooms into one very limited space. So the results could be shown up in all kinds of possible ways. So you could use Dynamo, you could use Fractal. In this case, they also brought it back into Revit and used this result as a plan to start building up the whole design of that model with spaces. Another example, and this is one of our customers in Denmark. It's a contractor called MT Højgaard. And what I have done in here is they use Dynamo, Format, Fractal, and Revit to configure parking houses. So the idea behind it is to create an optimal parking house, which is meeting specific requirements from the customers. And these requirements could be like the number of parking places, but of course also the cost. So how much does this parking house cost for that specific customer, right? So that they could know which would be the ideal one to position on that specific site where they wanted to have. Now, the parking houses need to be like sold to that customer. So they wanted to have the tool for the salespeople, a tool that is very easily accessible. So which could be like something on a tablet. So the sales guy, he goes to the customer, uses a tablet, shows the design in Format, and he gets like immediate feedback on that design if it's meeting the requirements of that customer, yes or no. Together with that customer, they could play a little bit with it, play with some parameters, and then get a specific design within some boundaries. Third step is to bring in all these design requirements into Fractal and then let Fractal decide which is the optimal solution in here to get to that specific point. Now, once you have these results, you of course also need to create a design for it. You need to create a documented model, which is Revit using in here, where Revit at least is used in here to perform the detailed design. So, this is an example coming from Format, where you have the layout together with, for instance, some site environmental things that come from big maps. Together with Dynamo Studio, they created a parametric system for that parking house, including columns, walls, beams, actually almost everything that is needed to create that concrete building for it. And these are all the several design options. that you have for it. All of these are shown in format, and that's something where everyone can work with if they just need to edit these sliders. So this is Fractal showing all the possible solutions, and then with the ideal solution we get into Revit, and everything is generated in an automatic way, reusing the parameters that were driven by Project Fractal. Using some mock-up tools, you can create then your nice architectural design to, for instance, create your building permit and then create your detailed design from it. So, let's have a look on the small video on it. As you can see, it's a very huge script, and it doesn't look very simple to build it. It isn't that simple to build it, but it's something, once it's built, they can use it for any possible parking house, as long as it's meeting some specific requirements, of course. But they build in a lot of flexibilities in there, like how the two bays within that parking house are positioned towards each other, the number of levels, the number of parking spaces they require, the way how you enter that parking house, and so on. So these are a lot of parameters that are taken into account to create this specific design. Now, what is very easy in here, and that's very specific for analysis, of course, is that you can use colors. So you maybe have seen it already throughout the presentation. Everything that is done in Fractal gives you colors like green, yellow, red, orange, blue maybe. You can choose whatever you want. It's owned by your Dynamo script, and in there you build in your own analysis. You build in how you want to represent the results of your analysis. And of course these colors give you much more IDs, give you much more flexibility, let's say, to evaluate your results. So again in here, after everything is generated, you see all the possible thumbnails, all the possible solutions. Of course, we know that everything that is green in here are the ideal solutions, or at least the solutions that meet the requirements of that customer. So by picking a few of them and combining them maybe into a new generator, then you can get even more detailed results from it. So at the end, you can save that file that comes from here. So you choose a solution, save it as a DYN file, which is a Dynamo file, and then we're going to use it to create that Revit model, right? Well, that was the only video I had from it. Okay, so another thing, this is like a project we are working on with Autodesk right now. It's still under construction, let's say. And the challenge in here is about creating a facade for a airport building. And the facade of that airport building has a very specific geometry. So as you can see on here, laser doesn't work. As you can see in here, the two sides, the two vertical sides of that facade are tapered, and the top, if you watch on top of that building, then you get like an arc. So we have like a very specific curved facade that needs to be panelized. Now, as an architect, it's easy to panelize something in Revit. You might say, okay, Dieter, use all the specific functions in Revit, like curtain systems or whatever, and create your curtain wall, and done. It takes like 5 minutes to build it. You don't need to build like complex Dynamo scripts. But then 3 months later, that design from the architect is approved by the customer, and so on and so on. It gets in the hands of a fabricator, and he comes up with like, yeah, no, this is not going to work. We cannot even fabricate it. Oh, why not? Well, your panels are distorted all over the place. We cannot even build it in a very proper way. You will have all kinds of workarounds that we will need to build those panels at that facade, and we will use some metal sheets maybe to cover all the gaps you have in between these panels. Then the architect will say, oh, no, this is the design, I wanted to have it like this. And then you have like these kinds of discussions which take like a lot of time to find an ideal solution, which is like a good compromise for both of the stakeholders. So what about if you could optimize, or if you could create already a facade that is fabricatable? Now, that was a question we asked ourselves on how to do this for this specific project. And of course, the solution was again Dynamo. Dynamo together with Fractal. While we were working on that project, it was like, no, I don't want to have like very simple panels. Let's make them very complex instead. Let's make them as complex as possible in that way that we don't have like horizontal lines, but these lines going from the right to the left are going up. So we have like tapered panels, and I want to have like 6 or 7 panels in a column at the left side, but I also want to have them at the right side. So which means that every panel in here has different dimensions. So that's a complexity in here. Now, we can parameterize that layout without Revit functions because I want to analyze all these panels. I want to analyze these panels against a few specific problems. One of the problems is, of course, is it torsed, yes or no? Do we have any torsion in that panel, or is it perfectly flat? We call this planar deviation. So if you have 3 points and you want to know if these 3 points are in the same plane, 3 points are always in the same plane. 4 points are not necessarily always in the same plane. The 4th point can be pushed back a little bit, and that's something that always happens if you work with specific panels, for instance, in Revit, if you use adaptive components, for instance. So, that's something that is done in that second step. It's analyzed against that specific problem, planar deviation. Another problem that you can have with paneling is that the angles between two lines, so you have 4 corners in a rectangular panel. Now, in an ideal situation, every corner is 90 degrees, but we are not in an ideal situation. So this means that every corner will possibly have a different angle, something between 85 and 90 degrees, so which might give you a problem again for the fabrication of these panels. So, making that analysis, it needs, again, design options. So Fractal comes in to optioneer all of these possible options and to find maybe an ideal solution, again, with these colors green and red. At the end, we can bring them back into format to see how the layout would look like. Now, you might think, okay, yeah, fine, we have grids, but what does this say about the fabrication readiness of each of these panels? Well, all these colors indicating specific results tell us how many customized panels you need. And what we found is that there are fabricators. Now in this case we are using panels from a company in Germany called Schuko. And Schuko have a very nice parametric system for facade panels, which is based on tripods. Tripods that are connecting the tubes in each corner, and these tubes have like a custom length. The tripods are like fixed elements with some holes in it. Now if we use these fixed elements, if we use these boundaries as or internal angle calculators, for instance, then we can find an optimal solution for it. Now let's go a step further on that. In this case, we are using a way to take these panels, bring them onto the facade, but every panel, instead of also having the different heights and widths, we also want these panels to be different in aperture. And what I mean with this difference in aperture is what you can see at the right hand. This sinus wave is represented by these panels by just changing a little bit of their geometry. So you get like dynamic panels. So the architect still has his freedom in design. At one hand, he can make like a nice aesthetic design, but he won't have any problems with the fabrication of it, because he used already fabrication-ready elements which are optimized in a generative design way, and which are at the second time also optimized in some kind of aesthetic way using computational design. So you might see more of this project later on this year on all kinds of social media. So where we are going to represent this whole workflow with videos and so on and so on. But I wanted to give you already some insight on that. People among you that follow like the Dynamo hands-on lab this afternoon might see some of this in live, where I'm going to show a little bit how we can play with these sine waves and so on. So, to conclude, if we look at generative design in the world of ASC, what is the progression we have at this moment? Well, the traditional design where we are recording decisions is done like this. Well, let me rephrase it. Traditional design is where we record the decision. Generative design is we are describing the goals plus constraints. So we have that old way, which is traditional design. We had that new way with that human plus artificial intelligence algorithms, which is the generative design. Now in traditional design, if we look at products, then we have Revit with its parametric modeling. Okay, so that's parametric design. You create a family, you put it into your design, and you change parameters until you get like a specific building for it. There is also visual programming. This is already something overlapping between traditional and generative design. It's where Dynamo comes in and where you can automate your parametric systems. So it makes it possible for you to automate all kinds of repetitive tasks. With Fractal, we are coming into the field of option generation. So optioneering, as we call it. That's where we start with generative design, actually. So you're still using your Dynamo knowledge, you put it onto the cloud, and you optioneer everything. The next steps is also where we are going to refine our design. So the design optimization. Design optimization, again, in the cloud solution. So we had that example with that space planning, the Mars Toronto office. And then at last, we also have machine learning. So machine learning, which we already saw this morning in the presentation of the future of making things. Now, where are we now? That's here, with Fractal. So the next two steps that are coming, and hopefully next year at AU, or any of the AUs around the world, we can talk to you about real cases about design optimization, or not really real cases, but cases where we have our products built in already to do that design optimization. So, that's it about generative design, and I hope to see you in one of the other classes today.